Hello everyone. As you know, Matlab is matrix laboratory. And when you work with Matlab, you need to know about matrices and vectors, right? So vectors are a special case of matrices. They are like 1D matrices. So we start with vectors, go to matrices, and we make sure that you know how to create them, how to manipulate them, and work with them. So here, let's say I want to create vector A, right? So I type in A equals. And when you want to create a vector or matrix, you have to type the values for them or entries for them inside brackets. So I create a matrix A with, let's say, 5 entries, and I go with 4, 6, 0, negative 8, and then maybe 2.3, whatever. Now, here, if I want to access the first number in this vector A, I have to say A of 1, not A of 0. As I told you, Matlab is different from C and Python, and the entries do not start from index 0, they start from index 1. And when you want to access a specific entry or entries in a matrix or a vector, you don't use bracket again, you use parentheses. Okay, so when you say A1 means the first entry in A, right? When you want the, let's say, third entry, you say what? A3. When you want the last entry, you can say A number 5. But you always don't know exactly how long the vector is, especially if you have not created it yourself or the size of it is changing in your program. So we typically either find the length of that vector, and we use the function length of A. It tells me it has 5 entries, so if I want to access this last one, I say what? A of 5. Or there is another way to do it without you running the command length and finding the length and then using it here. You can use the keyword end. And it's actually a function, not a keyword. And when you say end basically finds the length and then plug that number for you here. So when you say A of end, it will find it for you. If you want the last but one entry, right, in this case entry number 4, you can say end minus 1. So you can actually, this end is like a number. You can add or subtract. Of course, if you add something to it, it's not going to give you anything, right? So you see here, the fourth one was negative 8. Of course, if you say n plus 1, then it goes to after this, there is nothing, and you're going to get an error, right? But this keyword end, this function end, is very useful for many applications. So here is to access any entry from the beginning, from the end, or so on. Now, can you access a range of entries? So let's say I want to access first and second entry. Yes, I say A1 column 2. So here, this guy is called the column operator, and column operator is creating a vector for you, okay, which starts from the beginning number, and with some increment it goes to the end number. So in general, you can say the initial value, column, increment, or it could be decrement, column, end value. Okay, when you do that, it creates a vector for you, this column operator. So let's say I would say 1 with increment of 3 all the way to 10. So what does it give me? It starts at 1, add 3 to it each time until it gets to 10, okay? And it might stop before 10, right? So if I change this increment to 4, then you only go 1, 5, and 9. You will never get to 10 because the next number after 9 is 13, and you're not going to get there, okay? So at or before the endpoint, you will stop depending on the increment and depending on the initial value. So this creates a vector for you. So now when you say, let's say A1 to 2, what does it mean? First of all, as I told you, I expect 3 values, beginning, increment, and final value. Here you only see 2 values. When you only see 2 values, Matlab assumes you are doing this. With the default increment in Matlab, if you don't specify it, is 1. So when you say 1 to 2 means go 1 at a time. Okay, it means go 1 at a time, and I'll show you. If you say 1 to 5, And if you say 1 increment 1 to 5, the result is the same. So if you don't specify it, Matlab considers 1. Okay? Now, can you decrease from one number to the next? Sure. You can say 5 with decrement of -1 go to 2. You go backwards. Okay? So if you have a negative increment or a decrement, basically, your numbers are going to decrease. So now when I say A1 to 2 means it's the same as, so you see here, these are the first two entries of A, correct? 1 and 2. That's the same as I say A of what? 1 and 2. That's the same as I create a vector 1 and 2 and then say what's the value of A at those indices, and it says it's what? 4 and 6, right? So this 1 column 2 is equivalent to creating this vector and then calling A at those indices, right? Or if I say A with 1 increment 2 each time to go to end, means an end here is 5, means jump 1 at a time. So start with this one, jump, and then jump. So I should get 4, 0, and 2.3 here, and that's what you see. Okay, so you can access any number of values or entries in A that you want. Sometimes when you go from some beginning to end value, you don't necessarily have a specific increment. Let's say in A, I'm interested in entry 1, entry 2, and entry 4. Well, clearly there is not a constant increment here. So how can I access that? Well, as I told you, just pass a vector of entries 1, 2, and 4. What's the value of A at entry 1, index 1, index 2, and index 4? And look, 4, 6, and what? -8. So we can provide that inside a vector. So here we talked about creating a vector and accessing specific number of entries in it. Now, a bunch of more important topics. 1, when I created this vector A, if you remember, I typed all of the entries inside what? Bracket, correct? I created everything inside bracket. And to separate these entries, I used the space. Now, you can also use comma if you want. That's the same thing. If you want to separate them, you can also use what? Comma. That does the same job. Now, if instead of comma or a space, use a what? A semicolon. You still will get a vector with 5 entries. The difference is now instead of your vector be a row vector, now it is a what? A column vector. So instead of dimension of it being 1 rows, 5 columns, now it's 1 column, 5 rows. Okay, it's 5 by 1 instead of 1 by 5. So in vectors and matrices specifically, comma or a space means stay in the same row. Semicolon means go to the next row. So let's say here, now I want to create a 2 by 2 matrix instead of just a 1 by 5 or 4 by 1 or whatever vector. So I can say B equals, now let's say 2 by 2. The first entry is 0, the next one is 4. So that's my first row, 0 space 4. The next row, since I want to go to next row, I use a semicolon, is -1 and 3. Yes? So whenever you insert a semicolon, you go to the next row. Now, the important thing when you create a matrix is the number of elements in each row should be the same. So I cannot say something like this, because now my first row has 2 entries, my second row has 3 entries. It's not going to work out. Okay, it says the dimensions are not consistent. So make sure all rows have the same number of columns. Now, what's about the dimension of this matrix here, B? Remember, for a vector A, I use the command length. How can I get the size or the number of rows and columns of B? I use the command size. I say size of B. And it gives me 2 numbers. The first one is number of rows. The second one is number of columns. And I can change that so you can see. So here, let's add one more row, -4 and 8, right? 3 rows and 2 columns. So now if I run it, you clearly see. So size of B returns 2 numbers for you, 3 and 2. And if you want, you can say number of rows, correct? And number of columns is equal to size of B, and now each one of them will be one of those numbers. Okay, so that's how to get the size of a matrix. Now, let's talk about more important stuff. 1. Is there any way I can convert my matrix into a giant vector? We call it vectorization. So what I do is, you see here I have first column. Can I get this second column and bring it, put it below the first column, and convert my m by n matrix into a giant vector which is n by m? Can I convert it? Yes. All you do is you say B and then column, and that's it. This column operator alone with no number in it will convert your matrix into a vector. Look, you see B was this, and if you look at B column is the first column, then at the bottom of it is concatenated by the second column. Okay, and in many applications, I'll show you later, you need to convert your matrix into a vector. Okay, so here I have converted my B matrix into a B vector, and if you want, I can call this a new thing and call it B vectorized. Okay, so now this is a new variable, B vectorized. And now the question is, you could convert your matrix into a vector. Can you go back from this vector to the matrix? Sure. For that, I need a command called reshape. So I have to say reshape this B vectorized, and then pass to it the number of rows and number of columns, and let's call this maybe C. Okay, so if I exactly tell it how many rows and how many columns, I should be good. So here it has 3 rows and 2 columns, correct? Can this do the job for me? And look, compare B and C, side by side, they are the same thing, right? So by reshaping, you can convert a vector back to any size, any shape of matrix, as long as the number of entries in this vector is the same as the product of number of rows and number of columns. So I can make it a 3 by 2, or I could make it what? A 2 by 3, right? Or I could make it any other thing as long as the product is 6 in this case. So that's about reshape and vectorization. What else do we need to know? So what about eliminating some number from, or numbers from a vector or a matrix? Can I eliminate something after I created them? I don't want to clean the whole vector or matrix. I just want to eliminate a row, a column, some entries. So let's say in this case, B is this, right? Can I get rid of this last row or last column or anything like that? First of all, how can I access the first row in B? If I want all the numbers in the first row in B, how can I access it? Well, the way to go about it for a matrix, in order to access a specific element, entry, or a specific rows or columns, you have to use 2 numbers. Remember, for a vector, we used what? We only used 1 number, correct? We say A of 2, A of 4. For a matrix, you need 2 indices, the row index and the column index. So if I say B of 3 and 2, what does it mean? It means go to row 3 and then column 2, so the number should be what? 8, you see? Or go in B to 3 and 1 means what? Go to the 3rd row, but what? Column 1, so the number should be what? -4. Or let's say here, I want to access this one, 3. What should I say? It's row 2 and column 2, so I should say B of 2 and 2, and so on and so forth, right? So for each entry in a matrix, I need 2 indices, row index and column index. Now, if I want the entire row, I go back and use the column operator. So let's say I want the entire first row. What do I say? I say B is entire row 1, but columns is going to be column 1 and column 2. So one way to do it is this. I say what? Row is 1, but column is both 1 and 2. That's one way to access it. Another way, instead of typing all the columns that I want, I can simply say 1 and column. Okay, it means all of the columns for that specific row, and that would give you the same thing. Similarly, if I want the second column in matrix B, what do I say? I say B, the row indices and column 2. Now, which rows? Since I want the second column, it involves rows 1, 2, and 3. So I should either say 1, 2, and 3. That's one way to say it. Or I say 1 with increment 1 to 3, and you don't need to write increment 1. Or I can simply say what? All rows, column means all rows and column 2, and boom. Okay, so this is how to access a specific row or specific column. Now, if I want a minor of matrix B, let's say I want the first 2 rows and the first 2 columns. How can I do that? Well, I say B, columns 1 to 2, and rows also what? 1 to 2, and it only gives me the 1 to 2, 1 to 2 of B. Okay, so here you clearly see how I'm accessing anything in matrix B. Now, I want to eliminate something. I want to eliminate the third row in this matrix and still keep the rest of it, just eliminate the third row. How can I do that? Well, first of all, how can I access the third row? I should say B of what? Row 3 and all columns, correct? This guy. I want to eliminate this. So how do I do that? I set it equal to empty brackets. Anytime you set a portion, a part of a vector or a matrix, of course you cannot do it on everything you can imagine, but I'll tell you what conditions you need. But if you set anything to empty bracket, means get rid of it. Look. Did you see what happened to B? B was this guy. Now I said get rid of the third row, and look, now the third row, which was -4 and 8, is gone. You see? Or A, remember A was this line vector. Let's say I want to eliminate this entry number 4. So what do I say? I say A number 4 equal to what? Empty bracket, and boom, you see -8 is gone. Okay, so empty bracket always helps you eliminate the stuff that you don't want. Now, can I eliminate anything that I want in a matrix? No, because right now, let's say here, if I go back to the definition of B, which was this guy here, can I say B of rows 1 and 2 and column 1? This is equal to empty bracket. Basically, what I want to eliminate is 0 and -1 out of B. Can I do that? No. Why? Because the result of that is not going to be a matrix anymore. It has first column with 1 entry, second column with 3 entries. It's not possible. So you're going to get an error. So you can eliminate as long as the result of that stays a matrix or stays a valid vector, then you can do it. Otherwise, this elimination will give you error. Okay? So I assume I told you a bunch of things about rows and columns and accessing stuff in a matrix or in a vector, reshaping them and so on. Let's see. Mentioned end, mentioned elimination. Now let's talk a little bit more about matrices and vectors that are specific or special. Like what? So there are some vectors and matrices that are special matrices or vectors. Like what? Like let's say I want a vector with all numbers in it being 0. I want to create a vector of zeros. So I say A equals what? And here I use the built-in command called zeros. And then I provide the dimensions of that. So let's say I want 6 zeros and 1 row, 1 column. So it's a 6 by 1 vector of what? Zeros. Or I want it to be a 1 by 3, 1 row, 3 columns of zeros. Or I want a matrix. I want it to be a 2 by 3 matrix of zeros. So if you want to create a bunch of zeros only, you use the command zeros. If on the other hand you want all of these entries to be ones, you simply use the built-in command ones, okay? And it gives you as many ones as you want in any arrangement. So ones, zeros. Now sometimes you don't want a specific 0 or 1, you want some random numbers. So let's say I want a 2 by 3 matrix of random numbers. Then the command you use is called rand. Okay, that's one of the commands, not all of them. And it gives you a bunch of random numbers. Now, what's specific about these numbers? They're all between 0 and 1. And they come from a uniform distribution of probabilities. So the chance that I get any number between 0 to 1 is the same as I get another number between 0 to 1. So the chance that one of these numbers is 0.5 is the same as the chance of it being 0.3 or 0.8 or 0.9 or any other thing. Okay, so rand, the numbers coming from a uniform distribution of probabilities, PDF, right? Probability distribution function. That's rand. If you want to now, let's say here, I created a bunch of random numbers between 0 and 1. What if I want random numbers but not between 0 and 1? I want a bunch of random numbers between A and B. Let's say what? 4 and 9, correct? So if you want to create a bunch of random numbers between 4 and 9, what should you do? So if I want my random numbers to be between A and B, then instead of saying x equal rand, I have to say x equal A plus B minus A, the range of that the range that you are interested in, times rand. This one will create numbers because when the rand is between, it's between 0 and 1. When it's 0, you will get A. When it's 1, you get A plus B minus A, which is B. And when it's between 0 and 1, you get somewhere between A and B, correct? So let's say here, as I said, I want some numbers between 4 and 9. So what do I say? I say A equals 4 plus. The difference between 4 and 9 is 9 minus 4 times rand. Now, if I want a matrix, I say rand of what? 2 and 3. So now, what happens? If you look, all of these numbers are random numbers between 4 and 9. And if I run it one more time, the results are going to be different. Right? That's the nature of randomness, correct? You see here? Each one of the numbers is different from the rest of them and from the previous numbers. That's called rand. Now, it's not perfectly random. It's called pseudo-random. Why is it? We'll talk about it later. So you are really able to recreate these numbers if you know something called seed for this random generator. So it's not like perfectly random that you can never generate them again. If you know what we call the seed of this random generator, you are able to recreate the numbers again. So this random and other random commands in Matlab are actually what we call pseudo-random, okay, which means there is a chance to recreate them again. So this is about creating random numbers. Now, as you saw, these random numbers were all decimals. What if you want to create random numbers between, let's say, 1 and 20, or 1 and 100, or 0 and 100, but do you want integer numbers? So if you want numbers, let's say, between what? 50 to 100, or 40 to 100, what do you do? So what I do is I say 40 plus 100 minus 40 times rand, and let's say I want to create a vector, not a matrix. So let's say 5 numbers, 5 random numbers, or let's say what, 10 random numbers between 40 and 100. Clearly, you see, I can create them, but they are decimals. So if I want them to be integer, what should I do? I have to round them or truncate them or anything. So I can use the command round or fix or ceiling or floor, any of the commands I showed you in one of my previous lectures. And if I keep doing that, right? You clearly see each time it is giving me what? A set of different integers. Okay, so that's one way to do it. There is another way that you can do it, and that's the command randi. Randi has a specific format. You don't, it's not going to create it between 0 to 1. It is going to create it between 0 to a max number. So it's the max number, and then you have the size. So it's the number of rows and the number of columns. Okay, so let's say I want numbers between 0 to 25, and I want 6 of these numbers with 1 column. Okay, and if you do it again, you're going to get different numbers, right? But here you don't have really much of control over the beginning of the range. The beginning is fixed at 0, and you can check it here. Rand I assume it was 0, not 1, but we can always check it. Don't feel bad if you forgot something. It's between 1 to I max. You see, I forgot myself, and that's okay. It's between 1 to I max, not 0 to I max, and that's okay. So you don't have control over the beginning of this, okay? You have only control over the end of this, but of course you can add and subtract and create random integer numbers, but it acts again similar to rand, and it comes from a uniformly distributed, as you can see, pseudo-random integers. There is another rand command, it's called randn. Randn again creates numbers that are random. The difference is they don't come from a uniform distribution, they come from a normal distribution, and basically the average of those normal distribution is 0, and the standard deviation of that is 1. So the probability distribution function for rand, as I said, is these are the numbers between 0 to 1, and this is your PDF, and this is your x, or that random number that you create. So if I call this random number y, then the PDF of y is going to be uniform. You have the same chance between 0 to 1 for every number you choose. But if you use, for this, instead of rand, use randn, then they come from a normal distribution. So here you don't have the same chance for all numbers in the range. You have a normal chance where the average is 0, so mu of that is 0, and the standard deviation is 1. So the PDF for y versus y is going to look like a bell-shaped curve, where the average of that is 0, and as you get away from 0, you have a smaller chance for that number to appear. Now, how far this is going? It's about 3 to 4 standard deviation. So this is like mu plus 3 sigma, and this is about mu minus 3 sigma. Between these two numbers, you have 99% chance for the number to appear. These tails will go to 0 at infinity, but we never work with infinity. The 99.9% chance happens at 3 or 4 standard deviation, and this standard deviation for randn is 1. So your numbers are literally between -3 to 3, or if you want them to really be tight, you can say 4 standard deviations. So between -2 to 4 and 4, then you have a very, very high chance, 99.5 or 9, you can always find it, correct? And so you know the formula for a normal distribution, as you know, it is equal to 1 over, so you have here sigma times square root of 2 pi times exponential of -1 y minus mu divided by sigma, the whole thing squared, and that is divided by 2. So this whole power is in the exponential, okay? So when you are for standard deviation from the average, and if you in this case use sigma of 1 and mu of 0, you can clearly see the chance that you have outside for average, and I can easily calculate that for you. So it's going to be 1 over square root 2 pi exponential of this number is going to be negative 4 squared, correct? Because y is 4 sigma, mu is 0, so that is going to be 4 squared, 16, e to the negative 8. E to the negative 8, correct? Divided by square root of 2 times pi. This is the chance you have outside 4 pi, and you multiply it by 2 so that you get outside both of them, and that is your chance, 2.67, and you can subtract now 1 minus answer, that's your chance, 99.97 or 98. So inside this inside this range of negative 4 to 4, you have 99.97% chance of your number coming from this range. And you can always try that, okay? You can say randn of, or just randn. You see, you get the number between negative 4 to 4. Randn, this time give it some dimensions. Let's say I want 8 numbers in this range. And if you look at these numbers, none of them falls outside the range of negative 4 to 4. Barely even out of negative 3 to 3. Sometimes you might get, if you add more numbers, there is a chance you get close to negative 3 point something, but definitely outside negative 4 to 4, you barely get any chance. And if you look at these numbers, the ones that are closer to 0, they appear more than the numbers that are far away from 0. So you see numbers that are closer to 0 a lot more than the numbers that are like bigger than 2 or bigger than 3, right? Those numbers would appear, but not as much as the numbers that are smaller, okay? And their distribution comes from this bell-shaped curve. Closer to average, you have a better chance to appear. Further away from it, smaller chance to appear. So anyways, here I talked about creating random numbers, and it went to a tangent, but that's okay. You need to know these important topics. And here we talked about special matrix, random, and so on. We have others like magic matrix and so on. I don't want to get into detail of that, so if you want, you can look it up yourself for magic matrix and so on. Let's talk about the arithmetic of vectors and matrices. So can you add 2 vectors together, or subtract, or multiply, or divide, or so on? Well, for adding and subtracting, the 2 vectors have to be the same size. So if I say A equals, let's say 4, 3, 0, and negative 2, and B equals the same dimension, so 4 by 1 in this case, 5, 9, 7, and negative 1. Can I add A and B? Sure, there is no problem. I can easily add. Then each element in A is added to the corresponding element in B, as you can see. Or can I subtract? Sure, again, each element in B is subtracted from the corresponding element in A. So 4 minus 5 is negative 1, right? 3 minus 9 is negative 6, 0 minus 7 is negative 7, negative 2 minus 1 is negative 1. So adding and subtracting can happen between vectors or matrices as long as they have the same dimensions. So here, if I say, let's say, let me show you something that is also important. C matrix is equal to A column B. You might say, what are you doing? Semicolon, I'm sorry. What am I doing here? What we are doing here is called concatenation. I'm having matrix A to be, or vector A to be the first row of matrix C, and then I go to the next row of matrix C and say the next row is what? Vector B. So I'm concatenating A and B vertically like this. So C is now what? This 4x2 matrix. Now I can create another one, call it D. This time I say it's B semicolon A, or B semicolon 2 times A. Can I multiply a vector by a constant number? Sure. If you see here, the first row in D is the same as second row in C, both of them vector B. The second row in D is twice as much as A, right? So when I say 2 times A, I'm just multiplying every number in A, as you can see, by number 2, right? Or when I say A plus 3, what am I doing? I'm adding this 3 to every single number in A, as you can see. So yes, I can add a number or multiply a single number by entire vector or entire matrix. So I can say C plus 1. You see, this is C, that's C plus 1. Every number is added a 1 to it. Or 3 times C, right? Everything is multiplied by 3. So anyways, here I created 2 matrices for you, the same dimension, both 2 by 4. Now, can I add them together? Sure. They are the same dimension, no problem. I can add and subtract. So addition and subtraction is rather clear. It gets a little bit more difficult when we go to multiplication. Multiplication of matrices or vectors follows the multiplication rule, and it's not as simple as just multiplying element by element. In general, if you multiply matrix A by matrix B and get matrix C, you need some specific dimensions for A and B to be able to multiply them together. So if A is n by P, n rows and P columns, then B has to have the same number of what? Rows as columns of A. So if A has P columns, B has to have P rows by, let's say, another number of columns. It doesn't matter, maybe M. So the number of rows of second one and the columns of the first one have to be the same, otherwise you cannot multiply. Now what's the result of that? The result of that is going to be the numbers that are uncommon between A and B. So it's going to be n by m. Okay, and this is very important. When you multiply matrices, you always need to have this condition. Otherwise, it's not going to work. Okay, so when here, can I multiply C by D? The answer is no. Why? Because C is 2 by 4, correct? And D is 2 by 4. So if I have a 2 by 4 and another 2 by 4, you see these two numbers are not the same, so I'm not going to get anything, okay? So if you say multiply, you should get an error. And say dimension mismatch, incorrect dimensions, okay? Now here it is giving you a suggestion. Always read the error messages. Say instead you can use dot multiply. What does dot multiply mean? If I do that, this is called elementwise product. So what this one does is, instead of doing the actual product of matrices, what it does, it is doing the product of element by element in C and D. So look, this is C, this is D. What did it do? It multiplied 4 by 5, it got you a 20. It multiplied 9 by 3, got you what? 27. Multiplied negative 4 by negative 1, got you positive 4. Okay, so it's called element by element. Each element is multiplied by the corresponding element in the other one and give you the result. For this dot product to happen, you need to have both matrices the same size, just like addition and subtraction. It's called elementwise product. But as I said, if I want to multiply C by D, in this case, it's not going to work unless I do something. What do I do? Can I exchange the rows and columns in D in this case, and instead of D being 2 by 4, can I turn it around and make it a 4 by 2? How can I do that? By exchanging the rows and columns. So you see D is this, right? Now, one thing I can do to D is we call transpose, and you know that from your matrices. Transpose of D is going to be exchanging the rows and columns. So the first row is now going to be the first column, and the second row is going to be the second column. That's one way to convert D into its transpose, or the easier way to do it is simply use a single quotation mark. That does the same job as transpose. So now, can I multiply C by D transpose? Yes, I can, because now I'm multiplying a 2 by 4 by a 4 by 4, and what's the result? The result are those two numbers, in this case, that are on the sides, 2 by 2. And you clearly can see that here. Now, can I multiply D transpose by C? Well, remember, this is a 2 by 4, this is a 2 by 4, correct? Can I do that? 4 by 2. Well, no. This is a 4 by 2, this is a 2 by 4. So the result is a 4 by 4. Yes, so I can do that as well. So first thing you clearly see from here is, in matrices, you cannot change the order of product. The product of matrices does not have the commutative property. But you can also do transpose of matrices and carry out this product. And what it really does in product is element by element is different than the actual product, because what you're doing here is C, I, and J. The entry I and J in C is equal to what? It is equal to summation, okay, of what? You multiply row I of matrix A by what? By column J of matrix B, and the summation goes, K goes from 1 to P. So basically, you are doing a dot product between the ith row of matrix A and the jth column of matrix B. You do a dot product, or you add entries, then add all these products together, and that is going to be your what? Entry I, J of matrix C. So in this case, if you look, when I'm doing C by D transpose, what am I doing? This is C, this is D transpose. So when I multiply them together to get this guy, look at this first element. The first element is what? Is the first row of matrix A dot producted with the first column of D transpose. So if you do dot product between this vector and this vector, the result should be what? Should be 4D9, and it is. You can simply check it with the command dot. If you say, what is dot between 4, 3, 0, and -2, and 5, 9, 7, and -1, correct? The number is what? 49. By the way, there is a command dot in Matlab for doing dot product, and there is a command called cross. If you want to do cross product, you can also do that, okay? So you can say cross. Now, the cross, you need to make sure they are what? Of length 3, okay? So you cannot have 4 entries in them. As long as there are 3 entries, you can carry out the cross product, okay? So, anyways, that's the product of matrices, the properties it has, and so on, and the dot product. As I said, dot product means elementwise. So this is elementwise, this is actual product of the matrices, and each one has its own requirements. What about division? Can you divide matrices? Again, that's quite interesting. So here, remember, I had A and I had B. A and B are the same size. Can I divide them? No. I shouldn't, but apparently I do. It gives me something. First of all, division does not have an actual meaning for vectors and matrices, okay? division, we don't define division for matrices and vectors. So what is it that I'm doing? When I say matrix A divided by B, what does it mean in Matlab? In Matlab, this is equal to, instead of B, I'm using inverse of B, and I'm doing this, A times B inverse. Okay? That's what I'm doing. So I have to invert B and then multiply it by A. By the way, a matrix can have inverse. An inverse, as you know, means a matrix that if you multiply to your matrix from left or right, the result is what we call identity matrix, correct? So B times B inverse is the same as B inverse times B, and it's equal to the identity matrix I. By the way, let's talk about I very fast. So I, or identity, by the way, there is a command in Matlab for it, it's called I. Let's say I want a 3 by 3 I matrix, identity matrix. So I can say 3 by 3, or I can say simply 3. And it gives me an identity matrix. What is identity matrix? It's a matrix that has 1 on the diagonal, and everywhere else it is 0, okay? So what's the property of this important matrix? As you know, when you multiply I by any other matrix like C, the result is going to be C. So I in matrices acts very similar to what? To 1. When you multiply 1 by 4, the result is 4. So I is very similar to number 1 for single numbers, right? That's what it is. Ones, the one that has all ones in it all over the place, that is not similar to 1. Okay, I can show you here. Let me create a matrix F, just a bunch of random numbers, let's say 3 by 3. Now, when I multiply this I of 3, which is what you just saw, by F, the result should be the same as F, as you can see. Now, can I multiply a matrix full of 1s by F and get the same result? No. Of course, your numbers are going to be different, as you can see. So it's the identity matrix, this guy, this diagonal matrix with 1s on diagonal, 0 everywhere else. That's the identity matrix. And when I multiply a matrix F by inverse of it, the result should be what? Identity. Now here, how do I get inverse in Matlab? I use the command inv. So inv of F is this matrix. Now if I multiply inv of F by F, you see, I'm getting what? Identity matrix. If I reverse the order, I still can get what? The identity matrix. Doesn't matter. In this very exceptional case, the order of the product does not matter. In both cases, you will get an identity matrix. And you might say, okay, can I invert any matrix I want? An invert for a matrix is like reciprocals, correct? So in numbers, when you have 4, the reciprocal of 4 is what? 1 over 4. For a matrix A, the reciprocal acts like what? A inverse. Because you know, when you multiply 1 over 4 by 4, the result is what? 1. So here, when you multiply A inverse by A, the result is I, which corresponds to 1. Right? So that's the same as reciprocal, basically, for scalar numbers. It's inverse. Now, what condition do you need for a matrix to be inverted? First thing is, it has to be a square matrix. It has to have the same number of rows and the same number of columns. That's 1. 2, there is something about matrix, it's called determinant. Determinant of the matrix should be not equal to 0, should be non-zero. If the determinant of the matrix is 0, then you cannot invert it. Okay, so for invertibility, you need F to be square, and you need the determinant of that to be 0. What's determinant? Determinant, in very simple English, is the number of rows or the number of columns in the matrix that are linearly independent from each other. And you can look it up, the meaning of linear independence. So anyways, here I introduced to you the command determinants, the inverse, and so on and so forth. And now going back to the division. So here I had this A, I had this B, and I divided A by B, And although I expected nothing to come out, why? Because first of all, B is a 4 by 1, isn't it? 1 by 4. It's not a square matrix. So it should not have any inverse. As I said, this is equal to this A slash B is the same as A times inverse of B. But inverse of B should not exist because it's not a square matrix. But apparently something exists here. Let's just run the command inv of B. You see, it doesn't give me anything. So the matrix should be a square. So how come it did anything here? We'll talk about that in a second. But before that, as I said, there is something called dots. Remember, we had dot product, which was element by element product. Can I do A dot divided by B? And the answer is yes, I can. Let's take a look here. Can I divide A by B? Yes. What I'm doing here is I'm dividing each element in A by the corresponding element in B. Look, I'm dividing 4 by 5, I get 0.8. I'm dividing 3 by 9, I get 0.33. I'm dividing 0 by 7, and I'm dividing -2 by -1. So I can do dot product as long as the two vectors or the two matrices are the same size. But can I do something like this? This is quite interesting, isn't it? What happened here, I'll explain to you. By the way, you might be a little bit curious to see, instead of forward slash, what if I do A backward slash B, which is equivalent to what? Here I'm dividing B by A actually, and this is equal to what? B times inverse of A, right? What about backward slash? Is that going to give me anything? Well, ideally it shouldn't, because A does not have inverse. Remember, A is just a 1 by 4. So it shouldn't give me anything, right? It should give me an error. But look, not only it gives me something, it gives me a 4 by 4 matrix, which is completely different than when you divided A by B and it was a single number. So what is it going on here? There should be no inverse for A or B, and this forward or backward slash should not give you any result. What is it doing? Well, what it is doing here is called pseudo inverse, using pseudo inverse. What is that? So if your matrix is not square, if A is m by n, and m is not equal to n, so the matrix is not a square, then you cannot define inverse the way that you traditionally do in linear algebra. What you define for this matrix is something called a pseudo inverse, and you use it with A plus. It's not like a cross, it's like a plus. And A plus, there are two versions of it, left pseudo inverse and right pseudo inverse. If it's left pseudo inverse, let me type that. Left pseudo inverse. If it's left pseudo inverse, then it means when you multiply this A plus by A like this, the result is going to be identity matrix. If it's right pseudo inverse, then it means you have to multiply it from the right side to get the identity matrix. Okay, so it should be A times A plus should be equal to I. So we distinguish between the left and right. Now, what's the formula for this, let's say, left? So what should I multiply by A to get I? Because remember here that my A is not square. It's m by n. So if I want to multiply something by it, it should be something by m to make it happen. And I'll show you it is, and it's actually n by m, so it's kind of like a transpose. The numbers are not exactly like transpose, and the result is going to be n by n. Or in this case, the right one, since this is m by n, this right one should be n by m, and the result is going to be m by m. So the dimensions for this left or right is the same, and the definition, let's say for this left, is what? So what is it? So a plus in this case is basically you have to multiply from the right side to a to make it happen. So it is going to be there is an a inverse here to multiply by a, but you cannot do it, so instead use what? A transpose to multiply by a, and here you do also a transpose times a, and you invert it. So if you multiply that by a, clearly this thing is going to become a transpose times a inverse times a transpose, and this whole thing is now multiplied by a. And since these two entities are inverse of each other and both of them are square matrices, you know, when you multiply any matrix by its transpose, the result is always a square. So now here you're multiplying a matrix by the inverse of that matrix, so the result is always what? I. Okay, so this is called left pseudo inverse, and here the right pseudo inverse is very similar, but when you multiply a by it, it should give you the same result. So it should be something like this: a transpose times a transpose inverse. So when you multiply a from the left side by it, multiply this first element by the inverse of it, again it gives you what? Inverse. And they are not the exact same thing. So what you're doing here when you're dividing is you're doing pseudo inverse, because a and b, for this example I used, they don't have inverse. So when I say a divided by b, which is a times b inverse, there is no b inverse. So instead of b inverse, it is multiplying it by b what? Pseudo inverse. And remember, a was a what? It was a 1 by 4, and this one was a 1 by 4. So what's going on here? So here, this b, which is on the right-hand side, it follows this one. So it is going to be b transpose times inverse of b transpose. Okay, so if I write it, it's going to be a times b times inverse of b transpose. Right? It's the right pseudo inverse of b. This is b transpose. So now the dimension of it, as you saw, it's opposite, backwards. So if a is m by n, it's n by m. So in this case, since b is 1 by 4, the pseudo inverse is 4 by 1. So you have a 1 by 4, and you have a 4 by 1, so the result of this, whatever it is going to be 1 by 1, a scalar. And here I am showing you the result. So you see here, that's the right pseudo inverse of b, that is a, and when I multiply, that's the same as a slash b. Now this a backslash b, what it does, it gives you the solution to the system of linear equations ax equal b, and the solution here is going to be x equal a backslash b. Okay, the left division. This is called the right division, this is called the left division, or forward and backward slash. And the solution to a set of linear equation does not always exist, right? You know, it depends on this a, this coefficient matrix, and it depends on the right-hand side. So whether this is a square matrix, whether the determinant of that is 0 or not, there is not always a solution. And if there is no solution, then Matlab might return to you something that does not make too much sense. So, if the b, the right-hand side known values, are all zeros, so the set of equations is homogeneous, then either the solution x is all zeros as well when determinant of a is non-zero. If the determinant of a is zero, then you have infinitely many solutions. If b is not all zeros, so the set of equations is not homogeneous, then again, if determinant of a is non-zero, you have a unique solution, finite unique solution. If determinant of a is zero, then there is no solution. Okay, so you have three different scenarios: no solution, infinite solution, unique solution, and that unique solution could be all zeros or non-zeros. Unique solution only exists when this A is a square matrix with non-zero determinant. So here I'll show you an example, and sometimes this A, as I said, might not be square, which makes the problem under or over determined, where again there could be some infinite or no solutions. So here it depends on whether you're talking about this A to be n by n, x to be n by 1, and b to be n by 1. Then the behavior of this is quite interesting, because I can also invert A and multiply it by B. So this should be the same as A inverse times B, which is like also dividing B by A, as I mentioned earlier, correct? Divide B by A is like multiplying A inverse by B, but here you have to pay attention to the order that is reversed. Okay, but again, if this A is not a square matrix, it's a rectangular matrix, then what happens? So if this A is instead is an n by m, this is an m by 1, and this is an n by 1. Now what? Can I still do that? What happens in this case? Well, I cannot use A inverse times B because there is no A inverse. Can I use the A pseudo inverse instead? Are the dimensions going to match? Well, what happens is n is, as we know, it is a is an n by 1. What about the pseudo inverse? Pseudo inverse has opposite direction, so this is going to be an m by n. And when you multiply, you're going to get an m by 1 for x. Okay, which is different, right, than what you had in the past. So here, let me give you an example and clarify this a little bit more. So let's say I have two equations, 2x minus y equal 1, and then negative x plus 3y equal 4. So as I told you in other videos of me, if you have watched them, you can write this into a matrix notation: 2, -1, -1, and 3 times x and y is equal to 1 and 4. And here this matrix has non-zero determinant, as you know, and the right-hand side is non-zero, so it should have a unique solution. And that unique solution should be inverse of this A matrix times the B matrix, and I'll show you that, right? So here, what I will do, I define my A matrix to be 2, -1, -1, and 3, and my right-hand side to be 1 and 4. And now whether I say inverse of A times B, that's the solution. Whether I say A \B, that's the solution. Okay, there is no difference in terms of solution. The difference actually is if the number of set of equations gets larger and larger. Here you have to invert a matrix. Here it does not go through inverse of matrix. It actually uses the Gauss elimination method. And so in general, when number of equations is more and more, this method is acting way faster than doing it this way. Fine. And clearly, if you plug in 1.4 and 1.8 in these equations, you clearly would see that they would match, correct? Just plug in 1.4 and 1.8, right? So that's 2.8 minus 1.8, that's 1. And here is negative 1.4 and 3 times 1.8, which is 5.4 minus 1.4, that's 4. So it perfectly works. Now, sometimes the system of equation that you have is not completely determined. It's under or over determined. For example, if you make your matrix A to be a row matrix, it means you simply have this equation, 2x minus y equal 1. Then you can write it as this. Right? And now this guy here does not have an inverse. So what happens if I use that as A and this as B and I ask for a solution? What happens? So let's try that. So A here is 2 and negative 1 and B here is simply 1. And I say A back slash B. You see, it still gives me a solution, right? If I say inverse of A times B, of course it cannot invert A. But here it gives me a solution, 0.5 and 0, which is what? It says if you plug in 0.5 and 0 here, that's a solution. But that's not the only solution. You know, here you have infinitely many solutions. So what it did, it tried to zero out some of the redundant variables, some of the variables that are beyond the number of equations, and determine the rest of it. So it just gives you one single solution. And if you run it one more time, it gives you the same solution, okay? So that's for what? A system of equation that is underdetermined. You have more unknowns than the equations and you have infinitely many solutions. Sometimes maybe you add more equations than unknowns. So you have 2x minus y equal 1, negative x plus 3y equals 4, and then let's say x minus or x plus 4 or 5y equals, let's say, negative 7. What about this? This is now overdetermined system of equations, right? You have more equations than unknowns. What do you think would happen if you pass this to Matlab? So here, I'm going to change my A, add one more row to it, and the numbers are 1 and 5. And my B, I'm going to add one more column to that, and that is negative 7. And again, I run A back slash B, and you see, again, it gives me something. Negative 1.5 and 6857. Now, if you plug that here in these equations, so it was negative 1.5 and point what? 68 or 69, let's say. If you plug in here now for x, you have negative 3 and negative 0.69. That's not going to be equal to 1. If you do it here, right? Let me make sure my y is correct. No, my y is negative. I have to pay attention. This is negative. What happens here? That's negative 3 plus 0.69. So here this result is actually going to be negative 2.31. If you do this one here, this is negative 1.5. This is 3.45, correct? That's 345, 1. So this is going to be something close to -5. And this one is going to be something like, if you say 2, about -3.5. Completely wrong thing, right? And we make sure that we did A and B correct. So that's 1 and 5. We added a -7. So right, so completely giving me nonsense. Completely, because the system of equations is overdetermined and most probably, definitely there is no solution, there is no exact solution. What you need to do is to do least squares and try to minimize the errors, but you can never find exact solution in an overdetermined system. There is no way, okay? So you see this, whenever you do this A/B, Matlab will throw something at you, but it does not mean it is really doing anything meaningful, okay? It sometimes gives you garbage, and that's what we say a lot in engineering. Many times the robots, the machines, the computers, the software work in what we call garbage in, garbage out, GIGO mode. So be careful, not whatever you pass to Matlab and Matlab gives you back something means anything. Just keep in mind that when you say A/B or left division, it solves this system of equation if a solution exists. And forward / you also know the meaning based on the pseudo inverse, okay? So hopefully I could have clarified for you the divisions of matrices and vectors and multiplication, as well as the dots, divide, and dot product. Now let's very fast go and talk about the power, because that's also important. So I know the video is going long, but I want you to see everything that there is for matrices and vectors, at least to my knowledge. So when I have a matrix like A, can I say A squared? What does that mean? It gives me error. Why? Because A squared means A times A, and here A is not a square matrix, so I can never multiply it by itself. Here you have a 3 by 2. If you multiply it by another 3 by 2, the dimensions don't match. Now, can I say A to the power 2 with a dot? Yes. Here you are raising each element in A to the power 2. Okay, so compare A against that. You clearly see each element is raised to the power 2. But again, A square has no way to get it done unless A is what? A square matrix. Then you can raise it to a power. But if you want only the elements to be raised to some power, all you need is to use dot power. Okay, so I guess I mentioned that one, the element power. Now, there are some other very important things that we need to talk about. What are those? There are a bunch of built-in functions about vectors and matrices in Matlab, and I want to show the applications of some of them to you here. Okay, there are tons of them. I cannot, of course, cover all of them, but I want you to know. One was the transpose, or the single quotation. You also learn about the inverse and about the determinant. I mentioned the dot. I mentioned the cross. Correct? But there are others. What are they? I also mentioned ones, zeros, I. There are some others that I want you to know. What are they? For a matrix or a vector, you can use the commands min and max. If I have this vector B here, and I say what's the min in vector B, it gives me the minimum value. If I say what's the max in B, it gives me the maximum value, correct? So min and max work very clear on a vector. Now, can I exactly know where in this vector B this maximum is happening? At which index, at which location the min and max happening? Yes. The min and max can give you two outputs, not just one. So if instead of saying max of B equal to something, I can say max of B gives me two outputs. One is the max value, the other one is the max index. Then the first value is going to be the maximum value itself. The second one is the location where the max is happening. So here the second entry in B is the maximum number. So look here. You see the max value in B is 4, but the location it is happening is second entry. And I can run the same thing for minimum. Look. Where the minimum value in B is happening and how much is it? The first one gives me the value, the second one gives me the location. Minimum is -7 and it's the third entry that is happening. Okay, so min and max works very clearly, very easily on a vector. Now what about the matrix A? If I say where is min of A, what do you think it would give you? It's not going to give you this -1. I actually gave you two numbers. Let me, for the sake of education, change the definition of A and get rid of one of these -1s, replace it with something else. So make it -9 maybe. Okay, so now if I run min of A, you see it did not give me the smallest number in the entire matrix. What it did, it acted column-wise. It gave me the smallest number in the first column, the smallest number in the second column. So what if I really wanted only the smallest of the whole matrix? Then I can do it two ways. I can say min of A. So on this result, which is min of A, I run a min again, and that gives me the smallest number. Or before that, I can convert my A matrix into a vector, vectorize it, then run what? -9, the min command on it, or the max command on it. Because you know, when I vectorize it, now it's an entire vector. Okay, so clearly by vectorization or running the min or max twice, I can get the smallest number in the entire matrix. Now, what about the location of it? You might be curious. How can I know this smallest number is happening in row 2, column 1? You might say, well, you might be able to get what? Get again the two min value and min index from A. Well, let's see what happens if I do it. If I do it, again, it says min value is -9, -1, min index is 2 and 1. What does that mean? Okay, -9, -1, fine. What does 2 mean? It means the second location, the second index in the first column is that small number, and here is the first location, first index in that second column, that is the index. So it's not giving me really the location I wanted. By chance here, it is 2 and 1 also, but that's a separate thing, okay? So for example, if I change my A and let's make this -5, so I run it again. You see, although my smallest number is in row 2 and column 1, this guy here, 2 and 3, does not give me that location because it's for each column separately. So how can I get this really? Well, you might say, well, why don't you vectorize it first and then run min value and min index on it? At least the min value is definitely correct. What about the min index? It's 2. Well, 2, what does 2 mean in this matrix? 2 means what? Well, 2 means if you vectorize it, so bring the second column underneath the first column, then in that giant vector, the second element, okay, look, if you vectorize A, then the second element in that vectorized version is the minimum. Okay, Fine, but I don't want that. I want you to tell me in the matrix A itself, without vectorizing it, which row, which column is the minimum number. Can I use this 2 that it gave me and somehow use it for something? Yes. How? I should see this location 2 in this vectorized version corresponds to which row and which column in the original matrix. If I can find it, then I'm good. Now, how can I do that? Well, I have to convert my index to what? My index should be converted to subscripts or vice versa, okay? So here, this one will convert the index of a vectorized matrix, okay, with the size of that original matrix. It gives you the corresponding row and column. So the command to go about is called ind2sub. It gives you the row and column index if you give it the size of the original matrix and this location. So here, look, this is the location, min index. So this is what I do. I say the size I had for A was what? Even if you want, you can say size of A, right? That's the size of A, original A. And this index, I give it min index. Now look. It says it was row 2 and column 1. So in general, if I give you any matrix like this, how do you get the min value and the min location? You convert it to a vector and run the min command. It gives you 2 outputs. The first one is actually the smallest number. But in order to get the row and column for that number, use this index, okay? Use this index and then use it alongside with the size of the original matrix. Pass it to the command index to sub, and it gives you what? The corresponding row and column for that location. And you can do the same thing for max. Look, the max is happening here, correct? Row 2, column 2. So look, what I do is I run the command max here. It tells me max value is 3, and clearly it is 3. Now this index 5, I want to use it, so it tells me it was row 2, column 2. So look, max index with size A, where was it? Row 2, column 2. So that's how you find the location of min and max in a matrix. Okay, some other commands. Sum. If you apply sum on a vector, it simply adds all of the numbers in that vector together, like that. If you use the command prod, it simply multiplies all the numbers in that vector, right? 1 times 4 times negative 7. So prod and sum give you the product and the sum of all numbers in that vector. There is another command called diff. Diff, when you apply it to a vector, will subtract each number in the vector from the previous one, and it gives you the result. So it subtract 4 minus 1, which is 3, the negative 4 minus negative 7 minus 4, which is negative 11. So look, do you see that? That was B. This is diff of B, which is second minus first and third minus second. If there is a fourth, you will also get a fourth minus third. And this is very useful. Later we'll talk about it for numerical differentiation. Okay, so that's diff. Sum and prod. Now you might wonder what happens if you apply any of these to a matrix. So what happens if I say sum of A? Look at A, and what is sum of A? Again, it is acting column-wise. It's adding all the numbers in the first column. It is adding all the numbers in the second column. So what if you want sum of all numbers in A, all of them? Well, again, you convert it into a vector and then sum it up. And it is actually negative 9 because this is negative 1. This is positive. Well, if you add the numbers, these two would cancel, and you will get a negative 9, right? So that's 1, This is -6 and this is -4, so you would get -9. Or what if you do prod? Again, if you do prod and don't use vectorizing, again, it's column-wise. If you convert it into a vector and do it, now all numbers are multiplied together. And the same thing happens to diff and so on and so forth. One more thing, extremely powerful command for vectors and matrices and any operation on them, and that's called the command find. So let's say in this vector b, and let's make vector b a little bit bigger, so instead of just 1 for -7, let's add a bunch of other numbers. Right? You want to find out where is it in vector b that my numbers are bigger than, let's say, 6. Bigger than 6. Which numbers in this vector are bigger than 6? So now you are doing search in a vector. How do you do it? You say find where the elements in b are bigger than what? 6. And look what it gives you. It says entry number 4, entry number 6, and entry number 10. These guys are bigger than what? Bigger than 6. You might say, where is it that they are less than 2? Which locations b numbers are less than 2? It says 1, 3, 5, and 7, and look at them. 1, 3, 5, and 7. These numbers are less than 2. So it gives you the locations where this thing is happening. If you want the numbers themselves, not the locations, what do? You say you found the locations, right? Now give me the value of b at those locations. And now you get those numbers themselves. Okay, so the command find is very powerful, and you can add more conditions here. We'll talk about logicals in a separate video, but let's say you want numbers that are between what? Between, let's say 2 and 5. So you say b is bigger than 2, and use logical operators, and what? b is less than 5, and you have to use another parentheses and another one here. And it says, hey, it's only number 4 in b that matches such condition. Where would it happen? If you want, just use the find alone. It says it is in location 2, index 2, that this condition is happening. Okay, so you can really use this powerful command find. Okay, for matrices specifically, I guess I talked about inverse, determinant, ones, zeros. There are some other commands I want to mention for you here. One of them is trace. Trace is some of the diagonal numbers in a matrix. And the matrix has to be what? Square? Is that the case? Well, let's find out. So here A is what? A is not a square matrix. Can I write trace on it? No. It says matrix has to be square because you need to have a diagonal. So here I say A equals whatever it was, and to the right side of it, I add a 3 by 1 column. What is that column? 0, 4, and 10. What am I doing here? I'm creating a column vector 0, 4, and 10, and I say whatever A is, to the right side of it, add that column and make A a 3 by 3. You see? Again, concatenation. Now, can I run the command trace on this A? Sure. I simply add the diagonal elements, and that's trace. By the way, there is a command called diag. If you say what is diag of A, it gives you the diagonal elements only. So the command trace is like what? Sum of diag of A. Correct? Get me the vector of diagonals, add them together, we call it trace. And it's important in many linear algebra problems. There are other commands here, including rank, QR decomposition, LU decomposition, singular values, SVDs, eigenvalues, and so on. We'll talk about them later when we talk about math problems. So in my math videos, look for matrix decomposition, eigenvalues, singular values, and so on. And one other command I want to talk about is called repmat. This is a pattern of a matrix. So here, you see, I have matrix A, right? Now let's say I want to copy and paste another A to its right side. So what can I do? I either can say AA by concatenation, or I can say repmat of A and in a 1 row and 2 column format. So create a 1x2 matrix, and in each entry of that 1x2 matrix, plug in matrix A. Now I can make this more complicated. No, make it a 3x2 matrix, 3 rows, 2 columns. In each entry of that, make A. You see? If you see here, this 3x2 is A, this 3x2 is A, another 3x2, another. It's a 3x2 version where each entry of that is A. So here you can repeat a matrix along a specific direction and pattern and get your matrix repeated, and use this guy a lot. Okay, use this guy a lot, so we'll talk about that later. So these are some of important advanced topics. Now I want to make sure I have covered most of the stuff that you need, and just trying to make sure I give you everything that you need. So let's add a few more bonus material for you. Remember I told you the column operator, right? If you want to create a bunch of numbers, let's say between 1 to 20 with an increment of 2, you say 1 column 2 to 20. Then it creates a bunch of data for you which are equally spaced. The space between them is 2. So we call this data equally, or we call them linearly spaced data. Another way to do it is the command linspace. What's the difference between linspace and the column operator? In column operator, you provide initial value, increment, and final value. In linspace, what would you do? You provide the initial value, the final value, and the number of data points. In here, how many data points do you have? If you count, you see you have 10 data. So I can say between the initial value and the final value, create 10 data points equally spaced. Now, how much is that increment? You figure it out. Okay, now look here. What's the difference? You see, I still have 10 data. The distance between each one with the next one is the same, but I created them between 1 and 20, not in this case between 1 and what? 19. If I wanted to get that same vector, I had to say what? Create them between 1 and 19. then I would get the same thing. So what's the difference? Here, you don't know the number of data points right off the bat. The increment would tell you how many data points you have. Here is the opposite. You know how many data points you want. You don't know right off the bat the increment that you need. So let's say in a problem they say for you, generate 50 data points between 1 and 100 that are equally spaced. So you can simply say, well, variable c is equal to linear space between, let's say, 1 and 100, and I need 50 data points. If you see clearly, the size of c is 50, but the increment, if you look, that's not 2, right? Just you need to subtract, for example, c of n minus c at n minus 1. This is the amount of increments that you need to create 50 equally spaced data. Well, you might say, well, I can create 50 data points by saying go from 1 to 100, and the increment is the difference between them, which is 99 divided by 50 data points. Now, as you can see, this guy here, look at this. You see, you're starting at 1, jumping to 2.98, while last time you were 1 and you jumped to 3.02. And what's the size of this answer? If you look at it, it has 51 data points. Okay? So you aimed for 50, but you ended up with 51. Now, can you exactly determine the increment if you know the number of points? Sure. You can calculate that. It's not a big deal. But it's better, instead of you calculating it, you let linear space calculate it for you. Because linear space is doing that. It calculates the increment using the first number, the last number, and what? The number of data points. Okay? And there is a relation between the increment and the number of points if the initial and the final number are given. Okay? But again, each one of them has its own advantage. Whether you know the increment or whether you know the number of data points, I would use the linear space command or the column operator. There is another command similar to linear space. It's called log space. Log space, when it generates a bunch of data, the data are not equally spaced. They are logarithmically equally spaced. What do I mean by that? I'm asking you to generate for me a bunch of numbers between 1 to 10 and with 6 data points. So generate a bunch of data for me between 1 and 10, and I want 6 data points. Well, you expect this command to work, right? But you will be surprised. It's not. If you look at the numbers, the first number is 0, the next number is huge. I mean, look at this answer number 2. It's not between 1 to 10, it's 630. The third number is what? Answer number 2. Let me give it the name of a variable, AA. So now AA number 1 is 10. That's interesting, isn't it? AA number 3 is 39,000, and number 2 is 630. Right? So first of all, the distance between the numbers, clearly as you go from 10 to 630 and from 630 to 39,000, the distance is not the same. Second of all, I expected my numbers to be between 1 to 10. They are not. My first number is already 10. The next one jumps to 630. So what's going on here? You are creating n data points, but your data points are not between A and B. When you say log space of A, B, and N, It generates n data points for you, but the data are not between a and b. They are between 10 to the power a and 10 to the power b. So if you really want the data to be between 1 and 10, what should you say? Say 1 is 10 to the power 0 and 10 is 10 to the power what? 1. Now generate 6 data points. Okay, so just use the power of 10 here, not the number themselves. And now you clearly see I'm getting 6 data points between 1 and 10, and clearly the distance between them is not constant. As I'm getting toward the end of the vector, the gaps are getting bigger and bigger. How can I find the gaps? Using the command diff, if you remember. Look at the gaps. This is the first increment, second, third, fourth, and 5. But the distance between these points are the same if you apply logarithm to it. What do I mean? I mean, look, if I say what is logarithm of AA, instead of AA itself, let's show AA on a logarithmic scale. Right? These are the logarithms of those two numbers. And now run diff on this logarithm of AA. Now you see the increments are the same. Okay, so if you plot AA on a logarithmic paper, then the increments are constant. So we say these data are logarithmically equally spaced, not linearly equally spaced. And we use this also for controls and so many applications. We'll talk about this later. Just wanted you to know about log space. One other thing I want to talk about are three-dimensional and multi-dimensional matrices. So far, all you have seen was 2D and 1D, and 1D is the vector. So can I have a matrix that is 3D? Sure. Can I have a matrix that is 3D? Sure. Like what? I say E equals, look at here. In order to define it, you do it like this. You say all rows, all columns, and the first page or first plane of the third dimension is equal to maybe 2, 3, 4, and 5. Then the second page of that three-dimensional matrix is 0, -3, 1, and -5. And then the third page of that third dimension is 10, -30, 11, and 55. Now, if you look at the dimension of E, it's a 2 by 2 by 3 because it has 3 pages. Each page of it is a 2 by 2 matrix. Okay? You can see that here. So, and I can add more if I want. So I can add one more column here and then go to 4th dimension and 5th dimension. So you can add higher dimensional matrices. The limitation is this. The size of each page of this extra dimension has to be the same. So I cannot, for example, add a 4th page here and I make it a 2 by 1 instead of a 2 by 2. It's not going to like it. Say, hey, all previous pages were 2 by 2. Now you cannot add a 1 by 2 page. It's not possible. All of them have to be the same size. And you might wonder where in real life you would see multi-dimensional matrices, and I'll tell you, images. Any image that you see in real life is, at least the color images, are multi-dimensional matrices. Let me show you something. So for example, I say Matlab logo, right? And that's this image. And here I'm gonna go and download this picture, save it. Matlab logo, that's fine. And here I'm gonna show you what that Matlab logo is, which is here. I'm gonna read it as an image. I call it image variable. And remember, I told you I am read and I am showing the past here. I am read and it is called Matlab underscore logo dot ping. I read it into this variable image img. It added something for me. Image. That's okay. If you look at this variable, look at it. It's 599 by 667 by 3. Why? Because it has 3 dimensions. Each one of them is either the red, the green, or the blue values of that image. You know, images, we call them RGB, red, green, blue values. And each plane of the image has 499 by 667 pixels. If you want, I can show you that image now using the command imshow. Okay, and as you can see, this is an image. It has 599 in the height and 667 in the width pixels. And it has 3 channels: red channel, blue channel, and green channel. And if you want to only look at the first channel, which is the red channel. Look at the red values. Anywhere that is what? Whiter has more red to it. Anywhere that is darker has less red to it. I mean, green, blue, right? The same thing. So if you look at the second channel, that's the green channel. Again, darker means less green, whiter means more green. And you can look at the blue channel, right? Now here it might not be so easy to understand because in this image you don't see much of red, green, and blue. You mostly see orange and yellow, but here, let me show you some example that makes you understand it a little bit better. So, image, let's call it. So here I'm gonna read that again one more time to show you. So image is equal to imread of image.ping. Clearly see it is 227 by 222, but here there is no third dimension, so it means the image was not really an actual color image. It was really black and white. And let me see if I can get another image. Yeah, this is also black and white. For some reason it is saving it as black and white, so I have to use some trick here and show you, because RGB under downloads, JPEG file. So hopefully this is good. JPEG, and it is called RGB. So now if you see, it's 279 by 289 pixels by 3, right? And I can see that. Now if I say give me channel 1, look. Then the areas that had red, if you see them side by side, the areas that had more red, they are whiter. The areas that do not have more red, they are what? They are black. Correct? If I say now, show me the blue channel, then the areas that are blue are going to be high values, and the areas that are not blue are going to be lower values. And the same for green. So all the images you see in real life, as long as they have RGB values, they are all 3-dimensional matrices. Now, you might ask this question that you told us you cannot store matrices of different dimensions all under a large multi-dimensional matrix. Is that correct? Yes. So how can you store them? What if I really want to store 3 2x2 matrices and a 4x6 matrix all under the name of the same variable. How can I store that? We'll get to it later. That's using what we call cell arrays. Using cells, you can store heterogeneous data. Not only different dimensions, different types of data can all be stored under one single umbrella, one single variable name, and that is using cell arrays. And we are going to get to that, okay? So if that was enough, we can finish this lecture. Actually, I found just one more thing, and I want to tell you that. I feel so bad if I don't. Remember, I told you if I run sum on A, it does it what? Column-wise, correct? Now, sum can actually takes a secondary input. If I say, what is sum of A and 2? Now it did it row-wise. Look, some of this is 1, some of this is -2, and some of this is 6. So if I say sum A and 2, it is doing it row-wise. If I say sum A and 1, it is doing it what? Column-wise. So you can change the direction that it is adding the sum. But if you want it for all of it, then you have to vectorize it, okay? The same thing happens when you use the command mean. There is a command called mean, average, not min, mean. Here is the average of the numbers on each column, okay? And I can use 1, or I can use what? 2, to take the average of any row or any column. Again, if I want the average of all matrix A, I have to use what? Mean of A vectorize. Now, there are some new commands in Matlab. If we have them, sum2. We used to have a sum2, if it's still there. Okay, which does the 2D sum or mean2. Yeah, mean2 there is. Mean2 does the same job as I did for you here, vectorizing it and then taking mean. So what you can do is simply say mean A, but mean 2 of A. That gives you the same number. Now there is no sum2, but you can do it yourself. It's just a simple, there is STD2, but not that. And STD stands for standard deviation, which we'll talk about in a separate window on the separate lecture under math, statistics, and probabilities. Okay, line lecture. Thank you so much for being with me. Hopefully I can give you a bunch of important commands about matrices and vectors in Matlab. Thanks.